Today we're going to be talking about statistical conclusion and other types of validity, and I'll focus particularly on statistical conclusion validity as it entails specific features of study design and statistical testing that are quite common in different types of studies. So the first is statistical conclusion validity. What is it? This refers to the phenomenon when the conclusions of a research study are considered valid in that they are based on an adequate analysis of the data. And this type of terminology was originated in work by Cook and Campbell in 1979, who framed statistical conclusion validity, or SCV, as pertaining to the extent to which data from a research study can be reasonably regarded as revealing a relationship or a lack thereof between independent and dependent variables as far as statistical issues are concerned. So as a result, concerns about SCV have to do with the statistical properties of estimators, the features of the research study, and the aspects of the research design that are conducive to the development of appropriate inference and conclusions. So in other words, statistical conclusion validity refers to the extent to which the conclusions that we make from a research study, particularly those that are based using statistical estimators or different types of inferential tools from statistics, whether the conclusions that we make are valid and appropriate for the study at hand. Because if you think about it, if the conclusions that we make are inappropriate and they are used in, let's say, policy settings, this can have very dire consequences for how research and evidence-based research is disseminated in making decisions. So under Cook and Campbell and their 1979 paper, SCV focuses on the following three aspects. One is the statistical power of the study. Another is the type 1 and type 2 error rates of the study estimators. And the last is estimating the magnitude of the effect or impact confidently. So we're going to talk about each of these considerations of SCV in turn, and I'll try to give examples to illustrate what I mean by them in practice. So let's start with statistical power. Formally, statistical power refers to the probability that a research study will detect an effect if it exists. And this type of terminology and the idea of power is typically invoked in experimental studies in which we have a certain type of intervention or treatment, and the results of the intervention are compared against a control or a comparison group. Power refers to the extent to which a study will be able to detect those differences between a treatment and a control, again, if those differences exist. And because power analyses have been incredibly important in assessing whether a study is prepared or whether the conditions for a study make it well prepared to detect the results, it has been an incredibly important component of evaluation and experimental research, particularly in funding situations. And in practice, statistical power depends on three main things. One is the sample size, so how many participants or units are included in the study. The second is something referred to as an effect size, which is the magnitude of the relationship between the dependent and independent variable. So the effect size is specifically focusing on how large of a difference between the treatment and the control groups do you expect to see. And then finally, statistical power depends on something called the significance level, which is usually denoted by the Greek letter alpha in statistical problems. So let's first talk about sample size. In practice, the greater the sample size, the greater the statistical power. And this is intuitive because the more individuals or units that we have in a study, the more information that we are able to collect on the relationship between either the treatment and the control group, or more importantly, between the differences between these two groups and their particular outcomes. And so in terms of statistical analyses, a larger sample size is also associated with less variability compared to smaller samples, so that when we estimate differences between a treatment control group, the standard errors or measures of uncertainty are smaller compared to the types of standard errors that we see in smaller sample sizes. Now, in settings where the data are nested, power also depends on one additional thing, which is the sample size not only overall, but at each level of the nesting. So for example, in school settings, it is common to see students who are part of classrooms and multiple classrooms that are part of a larger school. And in this case, because students are nested within classrooms and classrooms are nested within schools, we have to consider in terms of power the sample sizes of not only the students, but also the number of classrooms as well as the number of schools. And the reason why this type of data structure is important is because students within the same classroom or even classrooms within the same school tend to show similarities either because of synergistic effects of their environment or because of similarities in backgrounds or the location of these schools compared to students in different classrooms or even students and classrooms in different schools. So to give a specific example, consider an online course on algebra where students are part of the same virtual classroom. And here, as I mentioned, students in the same classroom tend to be more similar than students in different classrooms, even in the same school or learning environment. And statistically, this similarity is represented by something called a correlation among the values of the dependent variable data collected from the students. And more importantly, a stronger correlation or a stronger extent of similarities among the students leads to less precision, which is in the form of larger standard errors. And when we have less precision, this leads to a decrease in power. So the takeaway is that when we don't have to consider studies in which there is nesting, or the nesting is not an important part of the study design, then the sample size, which is referring to the overall number of students, plays a direct role on statistical power. But when we have to consider the nested structure of the data, such as whether there might be similarities among students in the same classroom, our considerations of sample size then have to take into consideration the sample size at each level, because again, the amount of similarities that we observe tie directly to the precision of the estimates, which in turn tie directly to statistical power. So the second component that affects statistical power is known as the effect size. And the term effect size is traditionally used in experimental studies to refer to the magnitude of the impact expected, although effect sizes have also been invoked in observational studies in which we don't have a treatment per se, or at least one that is the same as what we would expect in evaluation studies. So for example, if a software program is designed to boost test scores by 5 points on average, the number 5 points is referred to as the effect size. In some cases, effect sizes are given in terms of standard deviations to be more comparable across dependent variables and measures. So something like 5 points might not be easily translatable to a different type of study in which the outcome is measured on a scale that is not based on points. And here, the idea is that statistical power increases as the effect size increases. The reason for this is that it is easier to detect something that is large compared to something that is small. And then finally, statistical power depends on the significance level, which among the three factors is actually the one that the researcher has the least control over. The significance level, or alpha, is a key part of statistical hypothesis testing. It is the criterion used to determine whether the results of a study are statistically significant, meaning that when we are examining the results of a study, we want to be able to assess whether the results that we're seeing are actually there versus being there just by chance. In practice, alpha is usually set to very small values such as 0.01, 0.05, which is the most common, or 0.1. And generally, when we design a research study, researchers aim for at least 80% power, namely that their study has at least 80% chance of finding a significant effect if it truly exists. So just to summarize this part here, statistical power is one component used to establish the broader statistical conclusion validity, and power itself depends on sample size, the effect size, and the significance level. But in practice, among these three components, researchers have the most control over sample size, which is probably why in a lot of studies we talk about recruitment efforts and incentives to keep participants in the study because of the fact that participants and their contribution to the study reflect the power of the overall study results. So in addition to statistical power, which is again a key component of establishing statistical conclusion validity, the second component has to do with something called type 1 and type 2 errors. Type 1 errors refer to the case when there is truly no effect, meaning that if we were to examine the difference between a treatment and a control group, there is actually no difference, so there's no impact. But in the situation where a researcher might conclude that there is an impact, this is one in which the statistical test is sensitive to a type 1 error. And in practice, this is sometimes referred to as a false positive, meaning that someone finds something when there's actually nothing to be found. Type 1 error rates are usually controlled, quote unquote, by the significance level that is set for a hypothesis test, which is why if you refer to my previous slide, when I talk about the significance level alpha, alpha is usually set to very small values such as 0.01, 0.05, or 0.1, because those are the probabilities that a researcher commits a type 1 error. And because many of us would like to keep the chances that we make an error as small as possible, we never see the alpha level be set to a value larger than 0.1. And in particular, if we set alpha to 0.05, for example, this implies that the chances of making a type 1 error, or the chances of having a false positive, should be no larger than 0.05 or 5% of the time. We can, of course, adjust the significance level. So if you were to choose a larger value, such as 0.1, then this implies that we want to keep a cap on the type 1 error rate to be no more than 10%. And different situations can entail different values of alpha, but in practice, it is always recommended to specify this alpha level ahead of time and to minimize the possibility of changing it throughout the course of a study or an analysis. Type 2 errors, which is the other type of error, refers to the case when there is truly an effect, meaning that there is an impact or a difference between the treatment and control group, but a statistical test for some reason does not detect it. And this is referred to as a false negative, in which there is something there to detect, but for some reason, because of the study or other circumstances, it goes undetected. And type 2 error rates are actually directly related to statistical power. In particular, the statistical power is the complement of the type 2 error rate. So when we say that we are aiming for 80% statistical power, that is the same thing as saying that we want to keep the type 2 error rate to be no more than 20% of the time. The third aspect of statistical conclusion validity is referred to as looking at the considerations for power and the controlling of type 1 and type 2 error rates. Specifically, if a research study is well-powered, meaning that it has at least 80% chance of detecting an effect, and there are no sudden deviations from the original study design that would affect the type 1 and type 2 error rates, researchers can derive valid estimates of average effects using either a statistical model or a certain combination of modeling and algorithmic based analyses. But in practice, there can also be multiple threats to statistical conclusion validity. And the first, which I'll focus on today, is the difference between sequential versus fixed sampling. So in classical research design, the sample size of a study was considered fixed, where it was either determined in advance, or any statistical analyses were performed only after the data collection was completed. But in some contexts, researchers do occasionally engage in sequential sampling processes where students or individuals are recruited on the go, and data that is collected up to that point is analyzed and may be used to inform further recruitment. Alternatively, a researcher may choose to stop data collection early if he or she has obtained the desired results. So in these types of situations, these represent threats to statistical conclusion validity, because we are essentially dynamically looking at the data or preemptively stopping the data collection for a goal that may or may not be the same compared to if we were to continue with the original study design. And in general, Sequential sampling, which is referred to the two examples that I just gave, in which the students or the recruitment is an ongoing process, or if the researcher decides to stop the study early, these both affect the type 1 and type 2 error rates, and more importantly, they can lead to inaccurate statistical tests and conclusions. These types of sequential sampling examples are sometimes associated with the somewhat derogatory phrase, which is data peaking. But more importantly, because of the effect that they have on the extent to which we can make valid conclusions, this practice is generally not recommended. Another threat to statistical conclusion validity has to do with multiple testing. And this refers to the phenomenon in which a researcher conducts several statistical hypotheses tests using the same data. And this is very common whenever a researcher collects multiple outcomes on the same population of students, for example, and performs a separate test for each outcome, even though they all come from the same population of students. And the reason why this is a threat to statistical conclusion validity is because it leads to an inflation in type 1 error rates, which again refer to the chances of making a false positive. Because the hypothesis tests are conducted using the same source of information, they are correlated by design, which affects the chances of one test finding an effect given that another test found one. So in other words, in this case, when we do multiple hypothesis testing on the same set of data from the same set of students, we are essentially increasing the chances that we find something there when there actually isn't something there to be found, just because we look at the data in multiple different ways, but ultimately it's the same data set. So to address this threat, there have been more formal ways of controlling the effects of multiple testing. And these actions to control the effects of multiple testing essentially revolve around performing corrections to the p-values from multiple tests. These corrections essentially put a penalty on the p-values for the number of times a test was performed using the same data. And these corrections are designed to preserve the original type 1 error rate, so the original alpha level of the study. And in practice, the most common correction is attributed to the work by Benjamini and Hochberg in their 1995 paper. So with that, I wrap up the section on statistical conclusion validity. And I would like to turn my attention to other types of validity that are also important sources of consideration in practice, but have been addressed in different ways in different types of contexts. The first is referred to as ecological validity. Another is predictive validity. The third is substantive validity. And then we have content validity. So ecological validity is a type of validity that refers to the extent to which the findings from a study apply to real-life situations. For example, do the results from a laboratory experiment on mice apply to human beings? Which is a very important question because a lot of the products that we might come across, especially if they are marketed for health reasons, are typically tested on non-human beings in the beginning. And ecological validity refers to whether the results that we see, for example, whether a medication that is applied on mice would be equally effective or might potentially be ineffective if applied to human beings. In predictive modeling, another example of ecological validity is referring to the sense in which a detector or a model predicting student behavior and whether it's constructed based on a virtual learning environment would also translate to students in a physical classroom setting. And this particular example is timely as during the pandemic there was a period in which virtual learning was the norm. An important question is whether some of the gains in student learning during that time would easily translate or be correlated with the gains compared to the traditional physical classroom setting. Next is predictive validity, which refers to the extent to which a predictive model yields accurate predictions of current outcomes, but also future ones. So this type of validity is usually very challenging to assess, as current data can be very different from future observations, even if it's based on the same populations. And in this type of validity discussion, you can think of something as simple as outcomes related to technology. And as many of us know, technology is an area that has been rapidly changing. So assessing the extent to which a model based on an outcome that is related to technology could be challenging when we're thinking about what happens over time, since something that was developed 5 years ago might even be considered outdated if we look 10 years from now. Another factor is to think about changes in environmental considerations. So if there are sudden shocks to a system, such as a pandemic or a recession, for example, then this also presents another challenge to predictability, as the circumstances underlying the data that is collected during one period, namely the time before the particular event, might be very different from the data that can be collected after the event. And this is related to sudden and traumatic events as well. So next, substantive validity refers to the extent to which the results of a study matter. And substantive validity usually speaks to the implications of the results and whether it will affect policies and practices. So for example, suppose data that is collected to identify the factors that predict levels of engagement in classroom settings focuses on one source of data, which is the choice of textbook. If information on textbook selection does not support accurate predictions of engagement levels, then this data source does not really contribute to the substantive validity of the model. Even though the choice of textbook might be one of several features that could be important in the development of a curriculum or in the construction of the materials that the teacher or the instructor wants to use in designing a class. And then finally, content validity refers to whether a test covers the full domain of ideas and constructs it was designed to cover. And here, suppose a study was conducted to assess the effects of a mathematics technology aid on improving students' understanding of algebra and geometry. Now, if the test was administered that only assessed for students' understanding of algebra but not geometry, then the test would have lower content validity compared to one that was more holistically covering both of the topics of algebra and geometry. And this is also related to the idea of construct validity, in which we are trying to design or to assess whether a tool or a model or a test is actually measuring what we want it to measure. So in this case, if we are specifically focusing on testing students' understanding of both algebra and geometry, then for the sake of both construct and content validity, we need to make sure that the test or the model is actually covering these topics instead of just one of them.